For today's discussion session, we will start learning about the expectation values of various field operators and their correlators in the given state of the field, and we will start our journey with the most trivial kind of state, which is a vacuum. Till now, we have learned about the strategy of quantizing any kind of field, and at the end of the day, we learned that the field itself becomes a set of collections of oscillator in momenta space, and associated quantity with the field comes with various kinds of structure. For example, a scalar field will just be oscillator in momenta space, and this chi q parameter which is appearing will become 1. There is nothing to associate it, it's just a scalar kind of thing. If it is a if it is a spinor kind of field, again I have oscillator structure with plane waves, but now I have a spinor part which gets multiplied over here. So spinor and spinor, two different kinds of spinors will be coming along. Similarly, for vector degrees of freedom, I will have another set of oscillators with PQ and PQ dagger. With this chi q now become the polarization directions. So depending upon scalar or spinor or vectors, we will have associated quantities like chi q's. Okay, so this is the generic structure we will see in quantum fields. Now, second thing is that all these oscillators operators, they have the standard operator algebra that A and A dagger have a commutation of identity. It so happens that the momentum degrees of freedom are continuous, so their identity representation is a Dirac delta function, while the discrete degrees of freedom, which will come either with a spin or the polarization, will come with a Kronecker delta. For a scalar part, this will not be present. Irrespective of whichever part we are talking about, whichever kind of field we are talking about, the Hamiltonian, the normalized, normal ordered Hamiltonian, apart from the divergent term, which always comes associated with this kind of fields, the overall above the ground state or above the vacuum Hamiltonian expectation value is obtainable from the rather the Hamiltonian operator is obtainable from the number operator in each mode and the frequency associated with that mode integrated over D3T. So this is the total oscillator energy for all sorts of oscillator which constitute the field for you. And as a corollary to that, the ground state of the full field will be individual ground states of all possible oscillator states. Remember, different oscillators come with a different label, momentum P, and let us say hyperspin, I'm tempted to call Q. For example, spinor field, it would be spins. For vector fields, it will be polarization. So collectively, I'm calling it hyperspin. Okay, so this is in a nutshell the strategy of quantum field is there. Now that we have a vacuum state at our hand, we can try to do some analysis of how the field will appear in vacuum and non-vacuum states gradually. So what is the property of the vacuum state? That is the ground state of all the oscillators put together. Therefore, it is ground state of the full field as well. And therefore, this is a normalized state. This is the state with which I start my business. So this is a normalized state. That means all oscillator state corresponding to level P and Q, they are normalized to unity. So all this individual ground state of oscillator PQ is normalized, and as an artifact of that, the whole vacuum is also normalized. If I can compute 0, 0, the thing, that is also 1. Okay, this state is a normalized state. However, if I start exciting modes in different oscillator modes, then I get states which are not properly normalized. For instance, if I take one particle excited state in oscillator labeled by PQ, momenta P and spin Q, and then I take another oscillator which is excited at momenta P primed and spin Q primed and try to compute the inner product between them, I will get, first I can write down the one P primed Q primed state as vacuum of that oscillator and then acted upon on that by the raising operator. Similarly, on the other side, the bra of the same thing is appearing will have this structure. And we know that there is a commutation relation between A and A dagger which is appearing over here, which I can flip the order of A and A dagger with a use of a delta function. So delta of Q prime, use this commutation relation here, delta of q prime, delta of p minus p prime, plus a dagger a would have appeared over here if I wrote like this. But a dagger a's expectation in vacuum will vanish because vacuum is no number excited state. Number operator is 0, or in other words, the A annihilates the vacuum for each of QP pairs. So therefore, I see that only thing I will be left with this expectation of this thing, and vacuum expectation of this operator in the vacuum state, and the vacuum state of this thing will not see any operator around. It is just identity operator, so they will be self-normalized. So I will be just left with the piece which is the delta function. And as you can see, if I make the two oscillators excited state p is equal to p prime, q is equal to q prime, that will give me the normalization of the state. That becomes divergent because p going to p prime is delta 0 is infinity. So I have single excitation has created me a state which is not normalizable. This is not a surprise because as we know, single excitation creates for me a plane wave. This is plane wave mode in position space. In oscillator space, momentum space is just first particle oscillator, one excited state oscillator. However, in physical space, you will see that it relates to opened up distribution in space, which is a plane wave. And we all know plane waves are not a normalizable state. So therefore, I realize this. So the state which we have generated, despite being localized in momenta, becomes opened up in position. This is the standard thing. X and p, since they are Fourier variables, right now they are not operators because we are talking about quantum field theories in which x and p individually are not operators, but they are Fourier related variables. Positions to momenta or Fourier momenta goes through a Fourier transform. And that property remains true as well, that if one is tightly localized, that means I have a delta function in distribution of position, then I get a delta function, I get a opened up plane wave distribution in momenta and vice versa. So that is what we are getting. We start with a definite momenta p. If I make it p and p prime, that means I know that state is p. The momenta of the state is definitely known to be p. There is no distribution about it. Therefore, the distribution profile in the momentum space is delta function, and its representation in positional space is a plane wave. And in either case, you can see that it is not a normalized state. So this is not a surprise. What we have to do, I have to smear a state with some smearing function. So let us say some uh, f of omega, and then, or call it p, and then I take this a dagger p, and this might be a normalized state of one excitation. But in a definite known momenta, if this becomes a delta function, then it is not normalizable. If I make it p minus p naught, that means this integration will just create me a state at p naught. This is not a normalized state because of this delta appearing. But if it is not a delta but a regular function, then it is a normalized state. So outcome is that normalized states of quantum field theory do not have a specific momenta. They have a distribution in momenta, and then there is a well-defined distribution, normalized distribution in position as well. That is what we would have expected of a wave packet in quantum mechanics as well. So only thing, we are now coming from quantum field theory domain. So I would not make a quantum field theory made up only one excitation. I should make my quantum theory, quantum field out of it, which are made up of many modes, and there is a weight factor to them such that the overall field's wave state is normalized. Okay, so that is how the strategy is to make states with excitations. Now we will go ahead and see what is the property of vacuum first of all to see before going to excited states. So now let's try to compute what is the expectation of a field itself in the vacuum state. This might be not very surprising for you because we have seen it before as well. So first let us write down the field in terms of its bare operators, the raising and the lowering operator. So you see I have written the field phi as the description which I had provided, d3p 1 over 2 omega p, and then these operators raising and lowering and the raising operator. I am writing here a and b dagger here. Most of the times the scalar or the vector fields we have seen a and a dagger appear. only for spinor fields we saw that two different operators appeared because we did not require the psi field in spinor case to be real. So I'm writing a general structure. If it is real, then A and B dagger, B becomes A dagger, meaning B dagger is A dagger. Otherwise, they are two different unrelated operators. So irrespective of whether it is A or B, the following is always true. If I take the expectation of any spinor or vector or the scalar field in its vacuum, at the end of the day, what it is going to happen is that all other quantities like this plane wave, like this chi q, like this integration, they will be just riding along. They will just remain like they are. Only operator in this game is this A and this B dagger. So only these operators undergo the expectation. All other things remain intact as they were because they are not operators of the state. Oscillator operators are these. These are just position space dependent quantity and extra degrees of freedom dependent quantities. Okay, so only the operators which get squeezed between the vacuum state is A and B dagger here, for example. And we know this operator annihilates the vacuum, so I'm going to get a 0 from this, and B annihilates the vacuum as well. That means B dagger with a bra 0 is also 0. This is just a Hermitian conjugate of that. So therefore this portion is 0 as well. So both the portions, this portion and the left portion of that are 0 individually. So I get a 0. Expectation value of the field operator in their vacuum is 0. There is nothing to be expected in the vacuum. This is a standard. That's why the name vacuum is there is nothing in the field. However, this is not as same as saying the field is empty. Despite having no expectation, there still can be things. Expectation is just like a mean value. Now we know of various distribution which have a mean value 0. For example, a Gaussian centered about 0 will have its mean value 0, but its other properties are non-zero. If something's mean is 0, it is not true that it is completely 0 everywhere else. So empty field would be completely 0 everywhere else. Non-zero, non-empty field with 0 expectation could be like a Gaussian. So therefore, one should need to look at whether it is only the expectation 0 or its other expectation values are also 0. For example, variance, whether it is a non-zero variance. This distribution which is completely 0 will have 0 variance as well. However, this kind of distribution will have a 0 mean but non-zero variance. So let us try to compute things. So variance of any operator we know in quantum mechanics, variance of any operator would be variance square, let us say, or variance is defined as a root mean square itself. So that would be operator squares expectation minus expectation square. So that means a double operator structure is required. First, here I have computed the single operator whose square is supposed to come here, and then two operators O and O has to be computed in the same state. Now, since we are talking about field operators, these are position dependent quantities. So better quantity would be, more richer quantity would be two different location operators, phi x and phi y. The limit x tending to y will generate variances like this, but it has a more richer structure that I can put two operators side by side in terms of two different position values, the position and space time value. So therefore, I'm going to obtain this quantity, which is a more general thing than the variance. It contains all sorts of fluctuations, not only same point fluctuations, but correlation points, meaning from this point to that point, x and y being different, how are they correlated kind of thing. So let us compute this object and see whether it is 0 as well. If it is 0, that means the field has no correlation, no variance as well, and it is flat kind of thing. All right. So let us try to do that. So again, I will write down the two phi's as two integrals of oscillator breakup 1, oscillator breakup 2. P comes with the first oscillator, P prime, label P prime comes with the second oscillator. Again, if you club together all the terms, you will have four kind of term. This going with the two terms of here, this second phi, and this also undergoing with the two terms of the second phi. So ultimately, I will have a four kind of terms, and therefore four kinds of operators which will be coming about. First, this A operator will combine with this A operator. Then this A operator will combine with a dagger operator here. Then there is this A dagger operator which will combine with this A operator here. And lastly, this A dagger operator will combine with this A dagger operator over here. So I will have operator A, operator A dagger, operator A dagger A, and operator A dagger A dagger. All of these quantities are getting squeezed between vacuum. So that means all these operators over here will be done expectation with respect to the vacuum. And now I know that this A acting on 0 will kill it. A dagger is not clear what will happen to them, so let us leave them around. This A dagger A within vacuum will also be 0 because A will kill this state. And A dagger in the vacuum again will be killed off because A dagger 0 from the left is 0. So only surviving term will be A dagger. Okay, and now I have this kind of structure. What do we do? Whatever we had done previously, I will convert this A dagger into A dagger A and a delta function. Delta function will come from the commutator. So I will flip this with the help of a commutator and I will get a delta of P minus P primed. So now I'm just for illustration, I am working with a scalar field. Q is put to 0. There is no Q. But if you are thinking about a spinal field or a vector field, be mindful of there is a Q also coming about over here. And there is a summation over Q as well. The two Qs, Q and Q primes. So be careful of that fact. Otherwise, all these things will go along together. This is just oscillator story, which oscillator with quantum number, which we have to sum over collectively. So what I have done, I have taken this pair over here, flipped it, and the delta function comes about, and then squeeze the whole quantity in the vacuum. When I squeeze the whole quantity in the vacuum, again this A dagger A inside vacuum, which we have known already is 0. I will be left only with a delta P minus P prime because the vacuum state is normalized. So this expectation of A dagger structure, which was non-zero, is non-zero with a delta function. It will give me a delta function in P and P prime. So one of the P primed integrations can be computed using this delta function. What will it do? It will replace every P prime to P, vector P prime to vector P. If that happens, omega P, which is just the magnitude of vector P, and omega P prime, which is the magnitude of vector P prime, will also become the same. So therefore, in this, the 4 vector P will become the same. The 3 vector are supposed to get same because of the delta function. The 4th component of the vector will become equal to each other because the 0th component entirely depends on the 3 component, the remaining 3 component, the spatial part. So ultimately P and P prime will become the same. The delta function's integration can be used to get rid of one integration and converting this P to P primed and omega P to omega primed. So ultimately omega P prime. So ultimately I'll be left with this and this quantity will become the same. This and this quantity will become the same, and ultimately I will be left with d3p 2 omega p e to the power I p dot x minus y, which is not 0. You can prove that this is not a 0. This survives. Okay. For any x minus y, this is not a 0 quantity. We will compute it explicitly what it is later on, but you can convince yourself that this is a non-zero number. So it is not a case of an empty field, because empty field would have a 0 variance as well. If I take x going to y, that is the same point correlation, this will become d3p upon 2 omega p. Some integration to compute, which will show you some number which is divergent, but that is another property of quantum fields. Same point quadratic operators or higher operators are divergent, and there is a regularization schemes people have to do on the same point correlators. Those stories are separate. That is the story of the fields and how the UV story of the field unfolds. We are not concerned over here because most of the time in this course we will not be concerned with the same point variance, but the correlator structure which will emerge handy in our computations later on. So you see, for non-zero x minus y, I will have a non-zero number. Even for same number x is equal to y, this is a non-zero number, but a very huge number. Okay. So therefore, I have a non-zero correlation in the field, non-zero variance in the fields. That means it is not an empty field. It contains something despite being called vacuum, because expectation wise individually it has nothing. If I compute the field operator, I do not get anything. So bottom line is the 2-point correlator is not just the product of the single time operator expectation. This happens for real numbers or classical quantities, right? If I have some quantity which takes value qt at time t classically, and q some other value qt primed, then I know the product of them qt primed. If this is 0 and this is also 0, one of them is 0, let us say, then the product is also 0. Classical operators, classical quantities satisfy like this: if either of them is 0, their product is 0. However, the product operator's expectation is not 0 when either of the operator's expectation is individually 0. So this correlator does not factorize like this. Okay, that is the hallmark of a quantum theory. They do not get factorized like classical variables. Okay, so the vacuum state is not a classical state in that sense. It has a quantum structure despite being empty. It does not follow the line of a classical thing. It has its own hidden quantum fluctuations inside it, and they might be important for certain processes. We will see many of the examples later on, but keep in mind, despite being named vacuum, it is not completely free of anything. It is not an empty state. It has correlations, but expectations are zero. All right. So now let us explicitly compute the quantity which we were claiming it to be non-zero and see for ourselves that depending upon x minus v's separation, this x minus v, by the way, is space-time separation. It is not the spatial separation. Remember, this dot product was between 4 vectors. So space-time separation, how does the 2-point correlator become 0 or non-zero? We have our reasons to believe that it is a non-zero quantity. So let us go ahead and try to do this computation explicitly. So remember, when we tried obtaining the 2-point correlator, we landed up with this integral which we have to perform. So let us go ahead and perform this integral. We have a d3p 2 omega p in the division. 1 over 2 pi cube should be there. Actually, I have missed out writing 1 over 2 pi root 2 pi by 3 everywhere. So each field comes with a 2 pi to the power 3 by 2 factor that we had seen long back as well. So I'm just maintaining this. So everywhere I have a single field will come with 1 over 2 pi to the power 3 by 2. A double field will come with 1 over 2 pi to the power 3, because two fields will have the square root quantities cancelling each other and 2 pi cube will be surviving. So I can put it over here. This is overall a constant. Do not worry, I'm just trying to keep it consistent with the notations of many textbooks. So if I write it like that, d3p 2 omega p would be there, and p dot x, which was appearing over here. Remember, in our notation, temporal part gets a negative sign, so I will have a p0 times delta t, so x minus y it was. So I'm going to write it as t minus t primed, and then the spatial part comes with a usual dot product in the spatial vectors. So p dot x minus y it is. So that is how the p dot x would be written, and symbolically it is given a structure gxy. This is called the correlation function, or sometimes the Wittmann function. So Wittmann function. Okay, now you can see from the face of it, everywhere p is undergoing integral, but p is depending on t minus t prime and x minus y. It is not depending t and t prime individually in a arbitrary fashion. It only depends on t minus t prime, and in the spatial part it depends on x minus y, which was the hallmark initially which we had written, that it depends on 4 vector x minus y. It is not a function of x plus y. It is not a function of x square plus y square or any other function. It is a function of x and y in a particular way, which is x minus y. So we could have written g. For vacuum state, it is just g x minus y. For other states, it might not so happen, because that depends on what integral I land up with. This integral is true only for the vacuum state. For other states, we have to see out of these 4 operators which we had seen over here, only a dagger was surviving. That gave me this. It might so happen that for other operators, other states, Many of these operators are non-zero, and ultimately I do not know whether I have a structure of as clean as this. This is true only for vacuum. Only for vacuum, the Whitman function or two-point function, despite coming individually with each field, at the end of the day becomes a function of x minus y. Keep that in mind, and we will see an example later on that in the next class, that this idea that g is a function of x minus y is only true for vacuum state. So I'm not writing it as x minus y, I am just maintaining it x comma y. Now for massless field, we know omega p is related to the magnitude of the spatial vector times c, that we have seen before as well. I'm not writing plus minus because plus minus part was already taken care when we were writing these quantities here and here. These included the plus minus parts. So whatever is appearing here has a definite signature, positive. So that's why the P0, which is omega P, has a positive signature over here. So let us write it down. I'm using C is equal to 1 unit as before. So what will happen? D3P, downstairs I should have a 2 times P times C, but I'm forgetting about C. C is equal to C is being put to 1. And this D3P vector integral can be written as in spherical polar coordinates as the magnitude of the vector P square dP, d cos theta and d phi, where cos theta, d phi, theta and phi are angles in x, y, z axis or I, j, k axis. So I can think of a arbitrary coordinate system. Some direction is I direction, some direction is j direction, some direction is k direction. And in that case, the d3p can be written like this. In this coordinate system's angular spherical polar coordinates. Now what I can do, what appears in this integral over here is this delta x vector. Delta x vector is x vector minus y vector. So I have decided to call t minus t prime to delta t, x minus y vector as delta x vector. Now given you can think of any point in space x, any other point in space which is y. So this will be x, this will be y in your initial coordinate system. So x minus y will be some other vector. Now what you can think of this new direction x minus y as your new z axis or new k axis. So that is what we have done here. We have aligned our k axis with delta x direction. Once point x and y are given to you, this is 4-dimensional point x and 4-dimensional point y, out of which I will pick out what is the position space x and position space y. Then I find out where is the x minus y direction. X minus y vector will be some direction. I start calling this as my new z direction. So that is what we have done. Looking at delta x vector, we have computed the direction of the z-axis in the new basis, and therefore I'm going to write down the angular integrals and other things, assuming that delta x is giving me the direction of z. So if that happens, then the p dot x appearing over here is actually the p's dot product with the z direction. So it will become p times delta x times cos theta. Remember, this is pointing in the z direction, its magnitude is delta x. So magnitude I'm writing this much. So p dot x will be px cos theta, p delta x cos theta. So far so good. I will just plug this quantity here as p delta x cos theta. Now I have a d phi integral to compute. Nothing in this integral depends on phi. It depends on cos theta. It depends on delta t. Nowhere phi has appeared in this coordinate system. So d phi integral in this coordinate setup will just go along without unperturbed, and 2 pi will come out. I will be left with only d cos theta integral and dp integral. P is appearing here, cos theta is appearing here. So that we have to do slightly more carefully. So first let us do the d cos theta integral. You can call this cos theta as y. Then effectively I have an integral of dy and e to the power ip delta xy. Okay. So if you do that, you will obtain this integral which is required as e to the power ip cos theta delta x divided by ip delta x between -1 to 1, and you can verify for yourself. You will get this structure: e to the power ip delta x minus e to the power I minus ip delta x divided by ip delta x. So next, we can plug this quantity of integral into the expression which I had. Now only this integral is left, this function is left, and the integration of this quantity and that quantity has been performed. So outside I will get 1 over 4 pi square. dp integral is supposed to be surviving, but see, there is a p coming from here which will cancel the p which was surviving over here. This p will be cancelled by the integration will give me this result. This p in the denominator cancels the p upstairs. What will extra it will bring? Iota times delta x will be extra. So twice iota delta x will be in the denominator. So the leftover integral is dp from 0 to infinity e to the power minus ip delta t, which was the other function which we have not touched, and the cos theta integral has given me this piece. So let us combine them both. So if we combine these quantities, I get e to the power minus ip delta t minus delta x and e to the power minus ip delta t plus delta x. Notice one thing, that delta t appears with negative sign in both the terms. Delta x appears with a fluctuating sign. In this term, it is coming with overall positive term signature, and in this term, it is coming with overall negative sign. This is like e to the power ikx integral, right? Integration over dk from 0 to infinity. X happens to be this function here and this function in the second term. But the structure is very similar, e to the power minus ikx kind of thing. And you know e to the power minus ikx gives back e to the power ikx with a ix minus ix in the denominator, where k runs from 0 to infinity. So exponential gives you back the exponential integral, and k quantity runs from 0 to infinity. So infinity in the exponential will give you e to the power minus I infinity times x, or in our case delta t minus delta x for the first integral and delta t plus delta x for the second integral. And this will be highly fluctuating function. This is the frequency is infinity. This will be rapidly fluctuating functions, and it is difficult to estimate its value because it is highly oscillatory functions. In any finite time duration, it will do so many oscillations that virtually everything will be cancelled out, and you will be left with some finite mean value it could have. So it is not a convergent kind of thing. This is not a convergent result. It is oscillating about some point. So what we can do in order to make it convergent, we can take its limiting convergent behavior. That is to say, whatever is the common signature term which is appearing in both of them, I'll go one step back and call that delta t I'm going to replace with delta t minus I epsilon. Okay, if that happens, both the terms get this minus I epsilon extra from the delta t part, and both the terms obtain e to the power minus p delta, e to the power minus p epsilon. At the end of the day, I'm going to put epsilon tending to 0 because I just want to get the result for only delta t. But as of now, I will just insert an extra minus I epsilon to make the integrals convergent. Now I have no problem because both the integrals e to the power minus I kx and e to the power minus ix primed, where this is x primed and this is x, both have this extra e to the power minus p epsilon. I have assumed epsilon is greater than 0, let us say. In that case, when I take the upper limit infinity, this exponentials will kill the upper limit. E to the power minus infinity is 0. So therefore, at the upper limit, the highly oscillatory kind of thing averages out to 0. There is nothing left from the upper thing. While for the lower limit, the things will survive. The lower limit, the numerators will become 1 for both of them. And remember, there is a sign difference. Minus iota appears for the first term and plus iota appears for the second term. And there is a plus delta x here and a minus delta x here. So only lower limit of this thing will matter, and that's what we compute. We will get this limit delta e tending to 0 because limit epsilon tending to 0, because that is what we want at the end of the day. Outside this 4 pi square times twice I delta x, we are giving me 8 pi square iota delta x, which I am going to maintain, and the integrals are going to throw up these quantities, iota minus iota kx and so on. So towards the lower limit 0, I will be left with this this uh, quantity which is surviving 1 over delta t minus I epsilon plus delta x. In the lower limit, this will become positive sign. This will come first, and the other thing will come second. This will come here at the lower limit 1 over delta t minus I epsilon minus delta x. You can combine these things smoothly, and you'll get the structure that is minus twice of delta x and denominator minus delta t minus I epsilon whole square minus delta x square. This is plain and simple algebra. And then you take epsilon tending to 0. Now you see a finite piece survives, and that is non-zero. This happens to be 1 over 4 pi square times the invariant space-time distance, d, invariant space-time distance. If you remember our discussion, ds square was something like this, minus dt square plus dx square. So this is finite. ds and dx were infinitesimal, and this is delta t and delta x. This can be two separated, physically large separated points as well, but it is Lorentz invariant quantity. So this is the structure of the 2-point function, or the correlator structure is 1 over d, kind of what is the space-time distance. If you try to bring the 2 point to the same, for example, getting the variance, this d will shrink to 0, and therefore this will blow up. That is the divergent part we were talking about initially, that any 2-point or quadratic or higher order operators in quantum field theory has a divergent pole always. That is called the UV pole. UV meaning short distance pole. Ultraviolet pole, the small wavelength limit or very high frequency limit. So this has a divergent structure in the 2-point being the same phi square kind of thing. So phi square x can be viewed as phi x, phi y, and limit x tending to y. And that is where the d will shrink to 0. Otherwise, for finite x and y separation, this is my non-zero number. The physical d, physical point separation between 2 points, physical distance separation, and therefore the correlation is non-zero over there. Even for same point, correlation is non-zero, it is divergent, but all other places as well, even at very far away distance, the correlation is non-zero. So this again leads to another kind of EPR kind of puzzle, how correlations are surviving at very large distance. Maybe this is the space life. I can think of a case where delta x is greater than delta t, c times delta t. That means there are no physical signaling between these points. Points are so soft separated that their distance in delta t amount cannot be covered by speed of light as well. There is no causal communication. Still, correlation survives. Correlation of quantum fields is not a causal effect. They are not generated from one point and sent to another point, because nothing can travel faster than speed of light, and this survives even after the domain of the speed of light. So this is just a genuine quantum structure. This is not classical thing. Nothing is classically traveling from one point to another. This is just inbuilt correlators in them. Okay, and this property, which is very unclassical and very significant, will become very important when we start discussing atoms talking to various kinds of field. Okay, now just to summarize things and wind up, for other kinds of field, you can do the same computation which we have done for scalar field. You can straight away do for vector fields as well. You just have to write AI and AJs with their appropriate indices. I is here and I is here. So I'm writing AI and AJ, not vector A and vector B. That also you can do. If I write vector A at location X and vector A at location Y, that also can be computed by writing this object as AI, EI. EI is the basis vector, this operator, and the similar thing for other one. AJ, EJ, summation over J is implied. So I'm first writing just AI, AJ kind of thing. You can multiply EI, EJ unit vectors to make the full vector correlator out of it. Okay. So the component of full vector correlators will be AI, AJ kind of thing. So just let me write it down once more. If I compute the full AX, AY correlator, I will get a structure like summation over I, summation over J, then this AI, AJ correlator which we are trying to compute. and then ei, ej, unit vectors. So this piece needs to be calculated, and that is what we are doing over here. I will write AIs like this, AJs like this. The same story will go through. Only one set of operator will be surviving across vacuum, A and A dagger. All other operators will be squeezed to zero between vacuum. And this time you have to be just careful to use the commutation relation appropriately. Previously we had flipped this with a use of a delta p minus p prime. Now you will have indices. Those indices, for example, for vector cases, we have realized that if they are the two-dimensional plane indices, then this is delta rs. But if it is three-dimensional I and j, they should satisfy the restricted completeness relation. They are not full delta ij, but projection from the full three-dimensional identity matrix minus the propagation direction. So this is the commutator which we had seen previously. We had previously written a lambda p, a p primed dagger lambda primed was delta lambda lambda prime and delta p minus p primed. If you compare our notes from the electrodynamics quantization, here lambdas were supposed to be polarization vectors along the plane, but if you insist that it should be on the three dimension full A, then this delta lambda lambda primed will be related to the three-dimensional completeness relation like this. This is what we had seen previously as well. So you do the same thing, you will get the correlator here ultimately like this. So Gij, which is being computed, is becoming delta Ij. So this is the extra piece you have to be careful under integration. Otherwise, this integration we have just computed. So you have to redo this computation with an extra delta Ij thrown up. First term will become exactly the term which we have computed. Second term, you have to be slightly more careful. Extra Pi, Pj, and P square pair has arrived. So do some business slightly carefully to obtain that. Similarly, for electric field, we can do the same thing. Electric field, remember, was obtainable from the derivative of this with a negative sign. Remember, this is in the so-called Coulomb gauge. And in this Coulomb gauge, electric field has to be obtained from the time temporal derivative. And temporal derivative will throw up minus iota omega p kind of terms as a common factor with a negative sign inserted in between. So that is what the decomposition we had written previously as well. Again, do the same algebra. Everything else will go through like whatever we have done for AIAJ, and ultimately electric field correlators can also be written like this over here. Here, omega p has appeared upstairs. Previously, it was appearing downstairs. This has happened because of a double omega p coming from derivative of each of the a's. This e and this e are made from time derivative of this and time derivative of that. That throws up extra omega pairs, and ultimately this brings omega p from downstairs to upstairs. So therefore, this is somewhat of a new computation, which is, but again, you can do the same analysis. The d3t integral can be broken into pi, 2 pi d cos theta and p squared dp kind of integral, and one has to compute that. I'm just writing it just for formal sake of structure that we know how to compute the vacuum correlations for electromagnetic field, both for vector potential as well as for the electric field. And similarly, one can write down for magnetic field as well. Okay. So we know none of the fields vacua are really empty. They are made up of the correlations. They are buzzing with correlations, and later on we will see that even for the empty spaces state as empty as vacuum, it is not completely empty. We would have artifacts of these correlations which will be visible in our physical considerations. Okay. So for vacuum, I stop here. In the next class, we will discuss about non-vacuum state of other kinds.